Optical property. Optical property is nothing but how the material interact with the light. That is the optical property. First, about the refractive index, it is nothing but it is a measure of how much velocity of light that is changes. It travels from one medium to another medium. So n is equal to v1 by v2, n refractive index. v1 is the velocity of light in medium 1 and v2 is the medium 2. This refractive index depends on first one energy and second one is properties of the material of the medium. Next, refractive index changes. In our work, we have chosen parabolic quantum lens made of gallium arsenide and gallium aluminum arsenide. Here, light is the incident along the z axis, so there is nothing but growth axis. Significance of the study, quantum well lasers are now replacing the conventional lasers due to their more efficiency. By adjusting the wavelength, even we can tune their very short wavelength we can generate. Here in formulation, this is the potential profile for parabolic quantum well. P of z is equal to V naught modulus z by L by 2 the whole square. Modulus z less than L by 2. V naught modulus z greater than L by 2. The railway function for the ground state is given by psi I is equal to a e power minus alpha square z square e power minus ar modulus z less than L by 2. B e power minus beta z e power minus ar modulus z greater than L by 2. Here a and b are the normalization constants and e power minus alpha square z square and e power minus beta is that which represents the what type of well is this and e power minus ar represents the donor. And next, this is the railway function for the excited state. Psi f similar to psi I. Additionally, rho is present here, which indicates the excited state. And A is the variation parameter, and A and B are the normalization constants, and alpha and B are the constants which can be find out from the following equations. That is alpha is equal to V naught divided by L by 2, the whole power 1 by 4. Beta is equal to square root of V naught minus EI. Babel energy state, Babel is nothing but without donor. So according to both Summerfield quantization rule, energy levels of an electron in a parabolic quantum well is given by EA is equal to 2 h bar divided by L 2 V naught divided by m star the whole power 1 by 2 n minus 1 by 2. Here h bar is the Planck constant and L is the well width and V naught is the barrier height. M star is the effective mass and N is the quantum state. In EI, I which denotes the electron in the barrel. This is the expression for the Hamiltonian. This will be converted into Rydberg unit. The last term will be changed. That E squared by epsilon of R that will be changed into 2 pi R. That is the interaction term. These are the parameters which we have used in the experiments. This is the expression for Hamiltonian integral psi star x sine d tau divided by integral psi star sine d tau. This is the expression for refractive index changes. These are the analytical expression for the first order and the third order changes in the refractive index changes. First one is first one expression for the first order, and the next one is for third order, and the last one is the total refractive index changes. Here I present only total refractive index changes. Next. We know divided by these are the physical parameters which we have used in our calculations. We know divided by these are the physical parameters which we have used in our discussion. Parabolic fundamental total energy for various values of parabolic fundamental will equal to 30 nanometer energy for various values of parabolic fundamental will equal to 30 nanometer energy for various values of parabolic fundamental will equal to 30 nanometer. It is also that total RAC is considered as non-linear. It is also that moreover RAC is linear as non-linear. It is also that it is noted that the total RAC has a crossover and energy of 4 and 9 has a value may be quoted as total energy value for low and high RAC. This graph indicates total refractive index this graph indicates for various values of benefit with their from the graph it is below that the total RSC is considered as a non-linear RSC. The total different RSC the linear term as a non-linear RSC. Here it is by the third order non-linearness. So the peak of the total RSC is all the reference peak of the total RSC and increase in all the reference peak of the total solutions. It is what we call the study the refractive index of the isotonic molar of gallium oxide and gallium aluminum oxide. Quantum well isotonic molar area gallium oxide for different aluminum concentrations. Our calculator will make that the refractive index strongly depend on the total energy, aluminum concentration and weight. And the non-linear and total RAC aluminum concentration is total energy and aluminum concentration. And our theoretical method provides aluminum data in the applications of optoelectronic devices based on the parabolic quantum well. Thus, the refractive optoelectronic devices will be acceptable for optical modulators and also equipment in the area of non-linear optical modulators and also
but they are concentrating more on the refractive index. They are looking at but they are concentrating more on the refractive index. But they are concentrating you can explain the refractive index. And third, to define this particular. We are trying to find the value of velocity around. And then can you define the velocity in some other way? We are trying to find the value of velocity around. But it is related to photons, electromagnetic radiation. So from that point of view also we can define the related to photons, electromagnetic radiation. So from that point of view also we can define the because for example cells, what is cells, electrical animation. So from that concept also we can define electrical animation. But linear, also from that from that point of view, also we can define factor, but you know, the velocity alone. From that point of view, also we can define the velocity alone. Where is the thermodynamic radiation? Okay, because so many equations you have derived. Based on different external point of view, because so many equations you have derived. Based on different external, you have shown that two-dimensional quantum laser. And if we have shown that why you have two-dimensional, so we have lasers. Quantum lasers were different degree order laser and quantum laser. Quantum lasers were different degree order laser and quantum laser. Quantum lasers were different degree order laser and quantum laser. I want that point. How it changes, how
By
it
understanding the
changes.
benefit of
I
exact
want that point.
generate even
How you define that? How
by
you
understanding
define that? Why you use the word
why it needed
how you define that? What is quantum? Why you use the word
ultimately that is the activity.
how much is quantum? Why you use the
Ultimately that is the activity.
word? We have quantum, quantum. You are using quantum. This kind of quantum. So much. You have three quantum. You are using quantum. This kind of quantum. So much. You have three quantum. You are using quantum. This kind of quantum. So much. You have three quantum. Other than so it can be around fully on that. Other than so it is that it can be around fully on that.
Congratulations, madam. A very nice presentation. I have some basic questions. Congratulations. You discussed about the Bohr's harmonical model. I have some slides. What are the drawbacks of Bohr's harmonical model? There are some drawbacks. What are the drawbacks of Bohr's harmonical model? There are some drawbacks. Drawbacks of Bohr's harmonical model. You could not explain the fine structure of spectral lines. You could not explain the fine structure of spectral. Thank you, madam. Now may I invite the next participant to present his paper. Now may I invite the next participant to present his paper. Ishwari. Now may I invite the next participant to present his paper. Ishwari. Now may I invite the next participant to present his paper. Ishwari. Now may I invite the next participant to present his paper. Ishwari. Now may I invite the next participant to present his paper. Ishwari.
So very good afternoon to all that are gathered here. This is Ishwari, who is scholar of physics, Janapayam College, Rajasthan, Telangana. I bring about the guidance of Dr. Sri Principal, Janapayam College, Telangana. And today I am going to present on the topic of the present and concentration of European growth. Today I am going to present the articles of the present and concentration of European growth. Today I am going to present the articles of the present and concentration of European growth. So these are all my outline of my presentation. Let us again chapter introduction, methodology, result and discussion, and finally conclusion. present this paper aimed at synthesis the European book contains example and nanoparticles hydrogen chemical composition for this paper CAFP plus minus 6 EUX O90 the X ratio will be 0.01 to 0.05 the objective will be to study the ratio will be 0.01 to study physical behavior by Wilson and to agree the magnetic property by Wilson. Next, I move on to my introduction part. Recently, M-type hexagonal ferrites have attracted a lot of attention because of their magnetic properties such as large magnetic resonance anisotropy, high proximity, great permeability, and magnetic resistance. Due to the aforementioned high proximity, great permeability, and high frequency devices, due to the following high frequency range, wireless communication tools, and local area networks. Mine was under the cadre of microwave operating markets because these properties make it necessary to be used as economics of microwaves or next, I go on to my methodology part. Initially, all the metal nitrates are dissolved in distilled water separately. All the metal nitrates are added to the we are started with water solution. Here, using multiple sets of fuel. Fuel plays an important role here. The role of fuel is used to increase the reaction and place ethnic glycol is added to the previous solution. Here, ethnic glycol is acts as a polymer which is used to reduce the previous solution. For example, this acidic polymer is added to the previous solution. Here, acidic acid is acting as an ingredient. All the homogeneous mixture are continuously there at particular temperature until the gel is obtained. The obtained gel was tried at over the at particular temperature with this one as obtained. The follower was isolated at the particular temperature with this one of obtained. The prepared lab was characterized by exactly this area in the model of the and the this is the exact pattern for my example. Exactly reaction takes confirms that there is synthesized items are infused based on all processes that reaction confirms that there is synthesized graph and applies the exact pattern was compared with the exit powder reaction pattern also. The exit form number becomes 85757. The major corresponding claims are 114, 117, 110. The major claims are 114, their version states that the average marks the size of the example for various ratios and the average marks the size of the 1 to 0.0. And the average particle size was calculated by using a base distribution. This was my HAR result. From this graph, I could analyze very clearly now that the shift factor by increasing the ratio analyze very clearly now that the shift factor takes place in a clear manner. This was my ESM results. The mathematician tells the source of ferromagnetic behavior and which have the high presence field values are found by changing the ratios, by increasing the ratio values are European value, the magnetization and the redundancy values decreases gradually. The high possibility value occurs when the ratio of x equal to 0.04. It was my everything result for example, which looks like a spherical shape. It was my everything result. This was my data result. Data set is also given. No impurity takes form to detect a transform of the sample. Finally, the transformation even though the various experiment have been prepared successfully by using solvent method, I see diagram diagram APIs data indicate the inner single phase wavelength structure for the magnetic research area indicates the inner single phase wavelength structure. This was applied in microwave.
Thank you, nice. Yeah, one of the questions. Actually, the part of the exit of the 0.4, average party percentage is the party percentage 48. Can you give the average party percentage is the party percentage 48. Sorry. Okay, maybe you have determined that it is 48 nanometer, but in all the other cases it is 44 nanometer. Maybe why you have determined that it is 48? Change occurs in all the other cases it is 44 nanometer. Maybe why you have determined that it is 48? Change occurs in all the other cases it is 44. That they have taken average in other cases also. For the average, they are also value increases from 0.2 to 0.3, the 0.5 the value increases, then automatically decreases. Can you give the reason for that? The 0.5 the value increases, then automatically decreases. Yeah. Can you give the reason for that? The 0.5 the value increases, then automatically decreases. Yeah. Can you give the reason for that? It's a phenomenon medium. What happens to that? It's a phenomenon medium. What happens to that?
Very nice presentation. You have used the solvent ethylene glycol. Very nice presentation. Will you try some of the solvent? Use the solvent ethylene glycol. What is the specialty of ethylene glycol? Some of the solvent. Use the solvent ethylene glycol. What is the specialty of ethylene glycol? Some of the solvent. Use the solvent ethylene glycol. What is the specialty of ethylene glycol? You tried the sample at 120 degrees Celsius. Have you tried with some other temperature? You tried the sample at 120 degrees Celsius. Have you tried with some other temperature? May I now invite the next participant, Pakira Parveen.
So, good afternoon, everyone. I'm Pakira Parveen of Studying MS Physics and Thermodynamics. I'm going to present the topic catalytic degradation activity of green synthesis, reduced graphene oxide, role in reduced graphene oxide. So in today's work, water scarcity is the most challenging problem, and purification and reusage of water is also an problem. So the main objective is organic pollutant degradation from the water resources. So, synthesizing the reduced graphene oxide, we synthesize the reduced graphene oxide by chemical synthesis method. Already the water has a dye ingredient. So in addition to that, we discuss the formation of hazardous byproducts. So we switch over to the which results in more toxic to our environment. So we switch over to the green synthesis method using the extract of endocarp, CDN diffusion and the reducing agent for the nanocomposites byproducts. So we switch over to textile industries, which plays a major part in the districts like Coimbatore and Tirupur. Textile dye affects the water bodies by inhibiting their plant growth and etc. The dye gets accumulated in the water resources, which prohibits the life of entering into the water resources. Therefore, the aquatic animals and plants gets dead, which or even pollute the drinking water to the communities inhibiting their plant growth and etc. The dye gets accumulated in the water resources, which prohibits the life of the environmental continuous pollutant will act as a reducing agent because of the presence of vitamin E presence. So this work reports the reduction of graphene oxide, silver and nanocomposites. This composite acts as a catalyst for the decomposition of methylene blue and methyl glycols. So the advantage of using the green was method is quite non-toxic, cost-effective, and eco-friendly for the production of nanocomposites. So we synthesize the reduced graphene oxide, silver, and nanocomposites by using the ACNO3 and HAUCl4 in the ratio 1:1 and mixing it with the graphene oxide dispersions. In addition to that, we add 10% weight of the extract of endocarp and distill it for 6 hours at 100 degrees Celsius and centrifuge it, wash it, and dry it for 80 degrees Celsius for 6 hours. The preparation of dye degradation is we are mixing a methylene blue with an NaBH4. In addition to that, we add our catalyst liquor enzyme and solution is still for different time intervals. And the catalyst is infused and the dye dissolution is viewed through the UV visible spectrometer. So this is the result of the discussion. The cell analysis of reduced graphene oxide. reduced graphene oxide silver nanocomposite, reduced graphene oxide silver and AG nanocomposite, AG and AU nanocomposite. The first one is RCO, which is a thin layer, and second one is AG, RGO AG, which is spherical in shape, and third one is RGO AG AU, which is also spherical in shape, and the second one has a diameter of 18.5 nanometer. And the exciting pattern shows the first A shows the peak of the graphene oxide, which confirms the presence of graphene oxide at 10.27 degree, and the second B shows the presence of reduced graphene oxide which has a peak in 24.5, and the third and fourth shows the presence of reduced graphene oxide AG and reduced graphene oxide AG and AU nanocomposites. The 3 and 4 are more or less similar, which shows no obvious difference. That is because of the presence of their lattice parameters, very close lattice parameters. So in order to confirm that C and D, we move on to the EDAX. The next level. So the EDAX, which confirms the presence of reduced graphene oxide AG and AU. So in this UV spectrum, the A red indicates the peak of a graphene oxide, which exhibits the carbon-oxygen bond due to the N5 star transition, and the B shows the presence of reduced graphene oxide, which has a peak at 265 nanometer, and the C, which is green, which is blue in color, indicates the presence of reduced graphene oxide AG, the presence of silver at 265 nanometer and 420 nanometers, and the D, which is green in color, indicates the presence of reduced graphene oxide AG and AU nanocomposites. So the degradation is studied for the methylene blue and methylene orange using these UV spectrometer, and the percentage is calculated using this formula. So now the catalytic degradation of methylene blue and methyl orange is shown in this curve. The first curve indicates the presence of methylene or degradation process of methylene blue by adding NaBH4. If we do it only with the NaBH4, the degradation process takes around 90 minutes. If we do it with the reduced graphene oxide, the degradation process is done in 25 to 35 minutes. If we do it with the reduced graphene oxide AG, if we add that catalyst, the degradation process is done in 25 minutes. If we add the catalyst reduced graphene oxide, silver and both nanocomposites, the degradation process is done in 2.5 minutes. So from this, the next slide. So from this, we confirm the presence of AU nanoparticles takes place. The degradation takes in 2.5 minutes by adding more catalyst. Similarly, the methylene orange, the degradation takes place in the same way by adding NaBH4. The degradation takes place along 90 minutes, and RG reduced graphene oxide takes along 35 minutes. For the reduced graphene AG, it takes along 20 minutes, and reduced graphene AgAU, it takes along 5 minutes for the degradation process. So from this we confirm. By adding the catalyst to it, it results in the degradation process by 5. From this, I conclude by saying that this is an environmental technique mixed synthesis method. Using this extract endogam of a selenium we can prepare reduced graphene oxide silver composite, reduced graphene oxide silver and gold composites. So this catalyst reduces the degradation process, where water gets where we can reuse the water and which results in the problem for the solution for the water scarcity. Thank you.
Nice presentation. Thank you for the presentation. Only one question. How do you prepare the RTO silver and gold nanocomposites? Okay, RTO it can be reduced. How we combine both silver and gold in the
Reduce graphene oxide with AG. In addition to that, we add silver composites.
first you prepare
First, we
RTO.
prepare reduced graphene oxide, and the second one is reduced graphene oxide with the silver nanocomposite. And in addition to that, we prepare the reduced graphene oxide with the gold nanocomposite.
What do you mean by nanocomposite?
It is a composition of both the two nanoparticles. Two nanoparticles.
Nano to nanoparticle.
No, sir, it is a composition of two nanoparticles.
RTO is also nanoparticle.
Graphene oxide is reduced into graphene oxide. The reduction of graphene oxide is That's the nano-composite.
What is the percentage of iron? What is the percentage of silver there? What is the percentage of gold there? Therefore, I ask this. So, nanoparticle we can add to 2%, 10%. So, there is a fraction there. So, therefore, I am asking how much this gold and silver can combine with the reduced iron. Okay.
Have you taken self-image, self-repeat as
Scan method, we use using the scan method on the instrument, we keep our sample inside, and under different degrees, we neglect accumulated images and we take that different images.
suppose if you take VDAX, you can see the percentage of silver, gold.
No, sir, according to the confirmation of exact pattern, there was no obvious distinction between the C and B. Using the reduced rapid oxide AC and reduced rapid oxide AC AU. In order to confirm that, we move to EDAX. So EDAX was not our first.
Uh, in the XRD pattern, you have shown A, B, C, and so on. A is the pure graphene oxide, and the next one, reduced graphene oxide. There is stability. What is it?
Bond oxygen molecules more reduced, so there is a reduction from 10 to 24 degrees, 24.7 degrees.
Okay. What are the other green dyes available? What are the other green dyes? Dyes. You use so many dyes. Methyl orange,
These two dyes,
methyl
red,
blue.
blue, and methyl orange.
What are the alternative for such dyes for your work? You have to think of the alternatives. Thank you.
Thank you, sir.
So, I thank on behalf of the Department of Physics, Ramananda College, Karumattur, I thank all the offline presenters, data presenters of today's session. Thank you.
Thank you, professors. Let's resume towards our technical session on recent trends in material science, RTMS 2023. I cordially invite Dr. S. Sebastian, Assistant Professor, Department of Physics, Alangal College, to introduce the resource person.
If your action inspire others to dream more, learn more, and become more, you are a leader, says John Quincy Adams. At this juncture, I would like to attribute this proverb to our chief guest, Dr. Sunil Kumar Avasti, because his valuable past makes him important today and it may impact the future generation. Yes, our chief guest is immersible resource and inspiring personality. He did his postgraduate from University of Lucknow. After completing his post-graduation, he joined the Photonic Research Group of Professor Usha Malaviya. At the Department of Physics, University of Lucknow, he completed doctoral thesis on optical device based on photonic research. He has published and reviewed more than 46 research papers in the international and Scopus Indus journals. He has frequented 19 international conferences and 4 national conferences. He is an excellent author. He has published books on engineering physics, volume 1 and volume 2. Really, he reached the pinnacle of success. Currently, he has more than 15 years of teaching and research experience. We have really privileged to have such a great and inspiring personality among us. On this auspicious day, now we are going to benefit a lot from him. Thus, to ignite our minds, now I request Chief Guest Dr. Sunil Kumar to deliver his message.
Very good afternoon to all. Very good afternoon to all. Could you please tell me my slide is visible to all?
Yes, sir, it's clearly visible.
Okay, thank you. And kindly clear one more thing, slide is changing or not?
No, sir, no.
Now slide is changing?
Yes.
Okay. Should I start?
Yes, sir.
Okay, thank you. So first of all, I would like to thanks Professor Wilson for giving me this opportunity and all organizers, all students for attending this talk. So today I'm going to discuss the biosensing applications of photonic crystals and why I have selected this topic to discuss amongst the students, because as we know, the day-to-day life of the people of the present world is dependent upon the various types of sensors. So the scientists are working hard to develop efficient, sensitive and cost-effective sensors so that best sensing technology can be easily available to serve the requirement of common person. Therefore, nowadays, photonics is one of the branches of the science which could fulfill all the expectations as well as challenges associated with designing of different sensors by studying the propagation of the light passing through the designed structures. So the today's talk is basically based on such issues, and in this talk I will discuss the basics of the sensors, classification of the sensors, then I will switch over the biosensors, how the biosensor works, and then I will connect the biosensing with the photonic structures. And also I will discuss how you will simulate the results using any computational software like MATLAB, Mathematica. So my talk is broadly, yes? Am I audible?
Professor?
Am I audible? Okay. So basically in this talk, I will discuss the sensor types of the various sensors, biosensors, how the photonic crystal, what are the photonic crystal, what are one-dimensional planar photonic structures, one-dimensional annular photonic structures, how to use photonic structures in biosensing applications, how we can create a defect mode inside a photonic band gap, or by creating a TAM-FANO resonance mode, and computational analysis pertaining to the planar photonic structures as well as annular photonic structures will be discussed. And finally, I will conclude the lecture by discussing how we can evaluate the performance of the designed biosensors. The first question which may come in our mind is what do we understand with the term sensors? So basically, what are the sensors? Sensors are the basically converter which measures a physical quantity and convert it into a measurable signal. This signal can be directly read by the observer or by the electrical instrument. There are number of examples around us. For example, digital thermometer is one of the example, and our touch screen mobile phone are the example. Piezoelectric sensors are such examples. Now we have digital weighing machine. Again, It is a kind of sensor. Basically, the sensors can be classified in two categories, that is active sensor as well as passive sensor. What do we understand by the term active sensor? Actually, the sensor which needs an external energy source to operate, like a microphone, a strain gauge, are the example of active sensor. In the passive sensor, this type of sensor generate their signal but do not require external energy, such as a photodiode and piezoelectric sensors. Then after discussing the sensors, I'm just going to connect the sensors with the biosensors. So the biosensors in which we may able to analyze, we may able to investigate the analyte or the sample which contain biomolecules are said to be a biosensors. So in designing a biosensors, we have a little bit idea about the physics as well as little bit idea about the biology. So biosensor, father of the biosensor was Professor Leland C. Clark. He has the first who invented the biosensors, and the basic components of the any biosensors are sample, which is in the term of biology it is called as analyte, the sample which contains a biomolecule under study. Then we have a transducer. It is a device which converts the energy from one form to another form. It contains two units. First is bioreceptor and second is electrical interface. If you see this bioreceptor as well as electrical interface. So in bioreceptor, the sensitive biological element are biologically derived material or biometric component that interact with the analyte. And in electrical interface, we have a detector element which detects the signal resulting from the interaction between analyte and bioreceptor and convert it into electrical signal. Then we have a electronic circuits, combination of amplifier, signal processor and display unit. So all these, the combination of all these three will form a biosensor as a whole. For having a good biosensors, we have all these points which must be fulfilled, all these requirements which must be fulfilled. First requirement is linearity, and second one is the sensitivity, then selectivity, response time, and reproducibility. All these categories will be discussed later. Then we can classify the biosensor in two categories. One is the bioelement, other in one is the transducer. This is a basically device and electrical interface. So when we talk about the bioelement, it is a antibody, it is a DNA, it is an enzyme or cells. When we talk about the transducers, so we have an optical transducer, we have a piezoelectric transducer, electrochemical transducer, and thermal transducer as well. So when we talk about the optical, we have a surface plasma resonance, we have optical fiber sensors, we have photonic sensors. Then there are a lot of applications of biosensing. So if you see, biosensing is applicable in environmental monitoring. It is associated with the soil quality testing. It is also applicable in food quality management as well as monitoring, pathogens discovery as well as detection, drug discovery, toxins detection, water monitoring, and disease detection as well. So apart from these applications, we have many more applications which involve these concepts. Am I audible to all?
Yes, sir. Yes, sir.
Thank you. Thank you. Now, so basically, first here I'm just going to give you an insight about the photonic crystals. Basically, what are the photonic crystal? These are the periodic optical nanostructure, and which can govern the propagation of light, and the mechanism of the photonic crystal is similar to that of semiconductor. In semiconductors, the role of the periodic potential will be similar to that of the role of the change in dielectric constant of the constituent material layers in photonic crystals. So basically, what we want to tell you, the photonic crystals are the engineered materials, and through which we can easily control and monitor the light propagation. So basically, depending upon the periodic arrangement of the material, constituent material into a photonic crystal, we can classify the photonic crystal in three basic categories. That is, if the periodicity of the material is along one direction, so we named as one-dimensional photonic crystal. If the periodic arrangement of the lattice of the constituent material is in two-dimensional, it is said to be a two-dimensional photonic crystal. If you see the second picture, so in this second picture, if you move along a y-axis, so again you are having a cylindrical rod of certain material that has been represented by blue color, and between two consecutive rods you are having a air space. That is how I am saying here the modulation of refractive index in x direction, as well as if you move along y direction, as well as if you move along x direction, again you will notice the periodicity, your refractive index of the material will change. That is through a material which has been represented by blue color rods, and between two consecutive rods you are having an air space. This is said to be a two-dimensional. Now, if this change in the dielectric constant or change in the refractive index is in along all three directions, we will name as three-dimensional photonic crystal. If you see the air holes, these air holes has been marked as this, you see whole layer arrangement, and here these cylindrical rods has been named as, you see, this is a rod layer, and we have a air cylinder as well. These holes are representing air cylinders. So what I mean to say is, if you move along x direction, y direction, as well as z direction, again you will move from one material to another material, then one material to another material, like that. That is why these are said to be a three-dimensional photonic structures. So some of the naturally occurring photonic crystal, that is if you analyze the feathers of butterfly or peacock, you will able to see there are prominent colors, and the concept why these prominent colors appears, this is because of the microstructures which are inbuilt into that structure by nature. And when the light incident on these structures, again constructive and destructive interference occurs between the light. That is why we are able to see these prominent colors. Then after discussing the planar photonic crystals, I am just going to give you the introduction about the annular photonic crystals. Basically, in order to understand the annular photonic crystal, you must have an idea about the cylindrical coordinate system. If basically what these annular photonic crystals are, these are the cylindrical concentric layers. If you see this diagram here, you may able to see there is fine hole is there. That means air cylindrical layer is there. If you, this is said to be an axis of the symmetry, or if you move away radially outward direction from this axis, you would able to see there is one layer of one material, then you have another layer material, then you have another layer of material, And these air materials, this here you are able to see the defect layer. That means the periodicity has been altered, periodicity has been broken. That's why you may have some other properties. I will discuss these things. So overall, in this diagram, what I want to tell you, what would be the nature of how you could able to observe, visualize what is the annular photonic crystal. That means, what is the annular photonic crystal? That means this is a concentric cylindrical layers having, if I move from axis of symmetry to outward, so we will have to penetrate, light has to penetrate the different material layers. This is said to be an annular photonic crystal. Now the devices, biosensors, which made up of annular photonic crystal, have a better high quality resonators for lasers, filters, and optical communication, and the sensing uh, capabilities of angular photonic crystal is also quite interesting, as well as because of their structures. So nowadays people are working on this angular photonic crystal. So I will explore the application of angular photonic crystal as a biosensors. Now again, this is the repetition of previous slide. That is basically biosensor. The basic parts of the biosensor are the physical component and biological component. So in physical components, you have transducer and amplifier. In biological component, you are having a sensitive bioelements as well as analyte. So now after having this discussion, now I'm just going to highlight how the 1D photonic structures, either it is a planar structure or it is a annular photonic structure, how these structure could be used for biosensing applications. Basically what happens, we all know that in photonic crystal, when light passes through it, there are some sort of frequency because of this periodic arrangement. There are some set of frequencies which could not be allowed to pass through a structure. This will be reflected by the structure. What another way, what we can say, the wavelength of the light, or we say frequency of the light, which falls into the band gap region, those set of light will not be allowed to pass through it. So scientists have thought that if somehow a defect will be created into the structure by breaking the periodicity. So periodicity can be broken by changing the refractive index of the material or by changing the thickness of the material as well. So what happens, there is a sharp tunneling mode, or we say resonant mode, will be appeared inside the photonic crystal. And another important point, the position and full width half maximum of this tunneling mode will be dependent on the refractive index of the defect layer region as well as thickness of the defect layer region. This property has been used in designing biosensors made up of photonic crystal. Now you see here I have tried to just show you one-dimensional photonic crystal. If you see green and yellow color lines are sheets are representing different material layers, but if you just reach over there, the red color sheet is representing air space. This air space is supported by another type of material to strengthen the localization of light. So this basically air cavity will be used to pour different kind of analyte, different kind of samples into this, and then again by having a transducer and some kind of materials, we can observe the change in the resonant peak inside the photonic band gap with the help of a computer screen. So next, now this is the conventional way of using photonic crystal as a as a biosensing application. The basic purpose is you must have air cavity. In that air cavity, some sort of analyte will be poured. When you pour the analyte, its defect mode will be moved from inside the photonic band gap, its reflectivity, its full width half maximum, all will be changed. And by recording this change, you can easily design, as well as you can easily develop photonic biosensor. So while adopting this way of this application by using a photonic crystal, you must break the periodicity and create a air defect. Another nowadays another work is also being considered. In this we have a conventional photonic crystal structure in which we do not bother to break the periodicity of the structure. Rather, breaking the periodicity of the structure, what we will do, we just put a in top of the either top of the photonic crystal or bottom of the photonic crystal. You can do it either ways. So you must create a air cavity, and on this air cavity you must have a thin metallic layer. So for doing this, we just consider a Krichmann geometry. Here a thin glass prism will be taken. On this glass prism we must pour a very thin metallic layers, and this metallic layers and the photonic crystal, there is some sort of a large distance is there, and this distance is in such a manner it does not violate the basics of photonic crystal. That is, the thickness of the layer should be order of the wavelength of the light to be incident on the structure. That is how you may again have a band gap, but in this time you are inside a band gap. You are having a resonant mode, which is called as TAM resonance. Basically, when we talk about TAM and Fano resonance, so at that point of time you must understand what are the TAM and Fano resonance. That is, TAM plasmons resonance is a way to localize the mode, could be obtained at the interface between the photonic crystal and thin metallic layer of having a negative electric permittivity. There in a Bragg scattering of photonic crystal and the negative permittivity of metal produce an exponentially decay of the electric field inside them. However, the high reflectivity of metal and the photonic crystal lead to a strong localization of electric field through the photonic band gap. Moreover, TAM plasmons resonance could be investigated at both under the normal as well as oblique incidence case, and there are many applications of TAM plasmon resonance. These applications are for gas sensing, biomedical sensing, optical filters, light emitting diodes, solar cell. So apart from the TAM resonance, we also have a Fano resonance, is another type of resonance produced by the interface between a narrow resonant mode as a time state and wide background of the photonic band gap. That means when we talk about the Fano resonance, it is at the intersection, it is at the interface of the TAM resonance as well as photonic band gap. At this vicinity you are able to get the Fano resonance. Here this photonic crystal, in this photonic crystal we have just used porous silicon materials, and here the porous silicon materials, here the porosity of the material is different. If you see the porosity of the material represented by refractive index N is quite less, with the porosity of material in the layer have marked by a refractive index N2. So if you change the porosity of the material, again refractive index will change, and that is interesting phenomena for the as far as the interest of the photonic workers, photonic engineers. Now when we talk about TAM and Fano resonance, then you must have the understanding what are the experimental setup which is required to which is required for observing the result from the photonic crystal. Again, this is a regular photonic crystal that has been marked by D1, D2, and just in front of this photonic crystal air cavity is there, and this air cavity we have some arrangement through which by the action of capillary action, the analyte will be liquid analyte will be poured into the structure which is under investigation. And we have here the first layer is a thin metallic layer. Then again we have a light source, we have a lens, we have a prism, and when the light falls on this prism, again it is dispersed in 7 colors. Then we have a slit as well as monochromator, and that is how the monochromatic polarized light is allowed to fall on this device. Then with the help of some sort of multi-layer fibers, multi-mode fibers, we could able to just catch the reflected light through detector, then on the into the monitor, and in monitor again inside the band gap we could able to observe some sort of defect mode. Again, this movement of this defect mode is quite interesting, and which will give you the important results. So finally, after discussing the TAM and phonoresonance based photonic structures, I'm going to discuss how to compute the results. So basically, in planar photonic structure, if you see, this is the planar photonic structure that has been marked by the refractive index of this layer, which is marked as A1, is N1, and refracted thickness is D1. Again, the refractive index of second layer is N2, and the thickness is D2, and its periodicity is sum of D1 plus D2, it has been marked by this Greek word. So that is how 1D photonic crystal will be formed. Yes. Am I audible? Any problem? Hello. Should I continue?
Yes, sir.
Okay.
Yes, sir. You can continue, sir.
Okay. Now you see, just we write a wave equation and just try to find out the solution of these wave equation. And by applying the appropriate boundary condition, we could have the matrix here. And when we solve this matrix, we would have the matrix element, that is M11, M12, M21, M22, and after getting these matrix element, dispersion relation can also be obtained. This dispersion relation is given by equation 3. If there are in audience, if some student who are working in the biosensing application of photonic crystals, I advise them to follow the book Born and Wood Principle of Optics. First 3 chapters are important. If you just understand these equations, you could able to formulate your problems. Now, for n-period structure, we apply a Chebyshev polynomial of second kind. After putting the value of Chebyshev polynomial, we can easily find the characteristic matrix or transfer matrix for n-period structures. And with the help of these 2 cross 2 matrix, which is marked by equation 4, you can easily find the reflectance as well as transmittance both. So if you want to see the details of this transfer matrix, so you can cite my paper. You can see this just published in 2023. The details are written here. Then after discussing the computational analysis of 1D planar photonic structure, I am just going to consider how you solve the problems, how you will just program the equation which is related to annular photonic crystal. So first of all, you see the cross-sectional view of annular photonic crystal. Remember that the pink region is orange region, I'm sorry, this is center region is representing the air cylindrical air hole, and this is cylindrical air hole, you are having a refractive index of material which has been marked by violet color, that has been marked as B. Then you have again concentric cylinder that has been marked by A, and AB you are having till this point, that is you are having AB to the power n structure. Then air cavity, which has been marked by green color, has been created, and this air cavity is supported by some other materials which has been marked by C, and again you are having AB to the power n structure is there. Now remember that this rho I is representing the distance from the axis of the symmetry to the interface between the layer. Here it is representing rho I is the distance of the cylindrical center of the cylindrical layer to the interface layer. So again, how you will change the value of rho I when you just program the problem, when you use MATLAB or Mathematica software. So at that point of time, here rho naught is representing the cylindrical distance, that is what is the radius of the cylindrical air layer, that is which is at the axis of the symmetry. Then you may easily, and each and every layer is of having certain thickness. So after adding rho 1 plus d1, you are getting the rho 1, that means then rho 2, then rho 3. That is how you can easily find the values of rho. Then after doing this, you have to write a cylindrical you must assume that there is a propagation of cylindrical electromagnetic wave moving radially outward from the axis of symmetry, that is the position at where rho is 0, which is z axis to the of the structure, and coming out through the cladding, which is of course maybe substrate. This means we can omit the derivative of the fields with respect to z axis. When you write the wave equation in cylindrical coordinate system, at that point of time you must write the change of derivative of electric field with respect to r, with respect to phi, as well as with respect to z. Since electric field is not going to be changed along z axis, that's why you may omit while writing the wave equation corresponding to TE mode in cylindrical coordinate system. You omit the variation of electric field with respect to z axis. Then after applying the variable separable method into that equation, you can easily find the electric field which is dependent on rho and phi. In this set of solution, you are having a Bessel and Newman function, and which are corresponding to azimuthal number m, and where k is omega square root of mu epsilon is the wave number of the propagating cylindrical electromagnetic wave inside the material, of the permittivity epsilon and permeability mu. And then after you are supposed to write the azimuthal part of magnetic field as well. And for writing this magnetic field equation, you are requested, you are advised to write the Maxwell third equation, and the Maxwell third equation is Faraday law, that is del cross E equal to minus J omega mu H. That is how you can easily find the magnetic field component. After finding the magnetic field, again you just write this for the annular photonic crystal of ith layer. You can define this matrix, and here the matrix elements will be, these matrix element will be, you see equation 3a, here y prime and y are, and j prime and j are nothing. It is representing the Bessel and Newman functions. Prime is representing the first order derivative. Then after having x,
Sir, can you finish within 5 minutes, sir?
Yeah, I'm trying. So that is how you can find these equations. And finally, after obtaining these equations, you can just find the transmission coefficient of 1D defective annular photonic structure with the help of this equation. And after doing this, you have the transmittance of the equation. If you have created a defect into it, you will get the there is a sharp transmission peak inside the band gap region. Otherwise, you may have simple band gap. So again, if you are interested to how this equation can be formulated, you can refer any one of my paper. I have mentioned one of my paper which is based on annular photonic crystal. Now after designing all these after designing the structure, you must analyze your structure, and the analysis can be done with the help of, there are parameters, few of them are mentioned here, that is sensitivity, quality factor, figure of merit, and limit of detection. Those who are working in the field, those such students are very much familiar with these important quantities. And here I have just tried to show you one of my design. Here the analyte can be inserted into the air cavity with the help of this inlet valve, and from the outlet valve this analyte can be extracted. So in this paper, I have just find out the protein analysis of the protein sample has been done in the crystalline phase of crystalline phase of GST material, and amorphous phase of GST material, because you see the cavity has been supported by the GST material. You see the red color lines are representing the GST material. So you see how the change in the crystalline and amorphous phase change the properties of the transmission properties, and of course sensitivity and all will be changed. So here all the numeric values are mentioned in this table. You can see that in this structure how the sensitivity varies, how the quality factor varies, and finally in the previous work in comparison to annular photonic crystal, you can see that in planar photonic structure the sensitivity of 130 nanomole nanometer nanomole per liter, and we have reported this extremely high sensitivity. This is all about for the this work. And finally, annular photonic crystal has a superiority over the planar photonic structure. First of all, the annular PC can be fabricated easily in comparison to planar PCs, and apart from the fabrication, we have other important parameters which are listed here. So these are the references from where I have prepared this talk, and thank you all from my side. If any questions, you are welcome.
Thank you, sir. Thank you, sir. Thank you for the nice presentation. Sir, thank you for the nice presentation.
Thank you, sir.
Sir, actually, there are two questions in the chat box. One is from Neela M. Is organic NLO crystal has sensor application? That is the first question, sir.
What is first question, sir? Please, could you please repeat?
Is organic NLO crystal has sensor application?
Organic crystal, yeah. We can use such a structure for organic as well as inorganic sensing.
Okay, sir. Then one more question, sir. From Amal Sundar. Sir, is there a common formula to calculate the refractive index of the defect layer based on the concentration percentage?
There is actually, as per my understanding, there is no common formula, but this concentration, if you want to find out the concentration dependent refractive index, so it not only it works not only dependent on the concentration, rather it also depends the size of the biomolecule, right? So this formula is a little bit complex, and getting this formula, we have to look towards the paper which is related to the field of zoology.
Okay, sir. If we can have a Maxwell-Garnett equation is there. Can we use that equation?
Yeah, you can use the Maxwell equation if you are interested for annular PC. So again, you have to write a Maxwell equation in cylindrical coordinates system.
One more question, sir. Actually, you have shown a formula AB to the power of n, then CDC AB to the power of n. There, D is the defect layer. C is the defect layer.
Actually,
what is the significance of C layer?
Yeah, you absolutely very nice. Actually, D is the defect layer of air, and this defect layer is surrounded by, from inner as well as outer, it is surrounded by a GST material. So if you coat this air cavity inside and outside with this one, so what happens? You have a 2 degree of freedom will also be added. If somehow, if a GST material will work in the crystalline phase, that point of time, the entire cavity effective refractive index will be another one. And when you just work it on a amorphous phase, that point of time you would have another refractive index.
Okay, sir. Thank you, sir. Some other questions also there. We will discuss in other time, sir.
Okay, thank you.
Thank you very much for the presentation. It's very nice. It's fruitful to us. Thank you, sir. Thank you very much. Okay.
Thank you, sir, for your informative talk. Now it's time for lunch. The next session will be started at 2:15. The lunch will be provided at Department of Physics. The volunteers will be guiding you.
Dear participants, if you have any doubt on the previous talk, you can put your questions in the chat box.